coming back to this second day. I see that around 300 are here, so I haven't scared off most of the people yesterday. So we'll continue from where we left off. Just a quick recap of what we did. We spent quite some time to talk about expectation values, because that is kind of the main thing on top of which error mitigations and everything are built. So and understanding how many circuits are executed for these kind of expectation value calculations, these are extremely important. So after doing those things, we started talking mainly about zero noise extrapolation. What was the main idea? That we have a quantum circuit, and for that quantum circuit, we can say that the quantum circuit is parameterized by some noise, lambda, and we kind of said that we are not going to put any mathematical definition or anything. Just give me a second. Yes, sorry. So what we said is that we are not going to put any physical interpretation of what is lambda, and we are not going to be too worried about how to exactly find lambda. But corresponding to the circuit, when we run the circuit, there is some associated noise. So we get some expectation value out of the circuit and the whatever observable we have. Let's call this E of lambda 1. Now we create some other circuits which are functionally equivalent with the original circuit but has higher noise. So call that, say, lambda 2, lambda 3, and we run the circuits again and again. And since the noise is greater in these circuits, we get worse results, and we take these as data points and then we extrapolate it back to get an estimate of what would have been the result if there were no noise in the system. And we kind of saw that we can do that with this digital gate folding. And we also talked about partial folding, why that is useful, where that is useful. And we also talked about the limitations of digital folding and why we need to go to this thing called probabilistic error amplification, where instead of randomly selecting gates, we look into an entire layer and we learn the noise of the layer. So that way we can throw away any extra, say this gate is better, this gate is worse, these kind of things we can do away with when we take the entire layer as a whole. What we will start with today is this assumption part. This is where we left off yesterday and said that we are not going to address this. We'll address this tomorrow. So let's start with addressing this. So you see, the point is that what we said here, that when you take this different noise profiles, when you look into, so when you are folding, as you increase, the nature of the noise remains the same. Unless it remains the same, so say it is going worse exponentially. That's something we showed. If you have, say, depolarizing or stochastic Pauli noise model, then it goes exponentially. So this kind of assumption that it's a stochastic Pauli noise model, how good is this assumption? This is something we need to discuss, and let's start with that today. Now, if you remember from last day, we kind of discussed a few things. What are the different types of noise that can happen on a quantum system? And let's just give me a second. Let's go back there. So what are the different types of noise that can happen on a quantum system? This is what we showed yesterday. Now here is one point. First, there is error in measurement. Do you take into account that? No, we don't. We said, I said that let's repeat the gates. That doesn't take into account the errors coming from the measurement. But I'll not be too worried about that, because we already discussed and we will show after this discussion that we can separately deal with measurement noise, and we will do that. That is not a problem. what are the different types of errors? Gate error. So roughly you can think that gate error is, say, depolarizing. Let's assume that it's depolarizing or stochastic Pauli. That means it goes down exponentially. It's that form 1 minus p rho plus something else, and as you increase the number of gates, it will go down as 1 minus p whole to the power k. So it's an exponential drop. Fine. Wait, there was a question. I think the question was something like, so I cannot really see the question with the screen shared. Okay, let's take that later when we take questions together. But is it the only kind of noise, the gate errors? Is that the only kind of noise? Even if there is gate error, this gate has more error. We know 2-qubit gates have more error than single qubit gates. So this is a problem. Second, the point is, here is another kind of noise that we discussed about, that if I put a circuit in, say, a qubit in state 1, that is the excited state, and leave it idle, it will spontaneously decay. Now the point is that this spontaneous decay is still exponential with time, but the rate of the rate by which this goes down for gates, the exponential decay rate of gates and the exponential decay rate of this idle time, they are not the same. And this is not really accounted for properly. Here is one problem. Well, okay, we can still say that, okay, this is also exponential decay, this is also exponential decay. What if we kind of take an average rate of decay, and we learn for, and we kind of take that, and the zero noise extrapolation works on that. These may have different rates, but these are still, both of them are exponential. So you can just take an average and take the average rate of decay or whatever it is. Fine. I mean, that is an argument which can be still made. Now, a second kind of problem. Second kind of problem. Okay, these are just examples. These are just examples. This is a G8Z circuit. I mean, this is something we discussed yesterday. This is a G8Z circuit whose ideal outcomes are all 0 and all 1. Ideally 50-50, but if you run it limited number of times, not infinite, a finite number of times, then usually we don't get 50-50, but we get very close to 50-50. But when we have noise, we get something other than that. These are just some example numbers that I have put down here. The other thing that we need to very strongly consider is, you remember something we talked about yesterday, that if you have a gate, a unitary gate, it's essentially a rotation. So, and the rotation is not perfect. If I ask you that you rotate by an angle theta, the quantum computer will evidently end up rotating by angle theta plus delta theta. So this is a kind of error that is called the over rotation. Now let's think of something. Let's say that, just follow this cursor here. I don't have an exact figure of this. Let's say that my quantum state was this, say pointing to the north, and I am supposed to put a gate which will rotate it to this side. Now, what I do is, instead of this gate, I end up rotating a bit more, so I end up going slightly slightly more here, right? The second thing is, let's say I was supposed to go here and I end up going here because I did some over rotation. So what happened? I moved away from the actual state. If I put another gate, there is not a single gate in the circuit, right? Usually we have many gates. If I put another gate, I say I am supposed to come here, but I again do an over rotation and I end up being here. So what is happening? I am moving away from the ideal state more and more as I put more gates. But this we understand, right? As we get more gates, since each gate is slightly noisy, the noise will kind of compound and we will move away more and more from the state where we want to reach. But remember, this is a rotation. So as we move away from the original state, what will happen? We will eventually come back. And after a few times, the the over rotation is actually taking you closer to the ideal state because it's a rotation. So initially it will go away from the ideal state, but eventually it will come back. And if you start putting more gates, it will again go away and it will again come back. So this is a periodic nature, a sinusoidal kind of a nature. Now here we get a problem. Here we were trying to make an argument that, okay, this is the depolarizing noise or the stochastic Pauli is a exponential decay. Here the decoherence is also an exponential decay. Even if the rates of these two are not the same, maybe we can take an average of the two rates or something. But suddenly we end up with a different type of noise, which is periodic. That has nothing to do with exponential. Now, think of this, that we are kind of saying that you take different noise profiles. As you increase your number of gates for the digital folding or PPA, whatever you do, as you increase your number of uh, gates, what will happen is the over rotation will increase. So there will be an exponential part coming from the depolarization noise, and there will be an periodic part coming from the over rotation of the gates. Now, how do you really extrapolate? We kind of argued previously that, oh, it's always an exponential decay, so you can always take an exponential extrapolator, and just for the sake of stability you can take a Taylor series and you can kind of truncate it for linear or for quadratic. These all things come from the assumption that this is an exponential noise model. But the moment you have exponential and a different kind of noise giving you a periodic, you cannot take both of them, and there cannot be a single extrapolator, there cannot be a single curve which can properly fit this noise. So this fitting that I showed here, it will not be so simple. In fact, maybe the things will not just get bad. Maybe what happens if it gets bad and then it gets better? How do you properly fit this? So all these things come into play, and this assumption is a strong assumption. We cannot have this assumption. So now we need to look into something which is kind of, what to say, it kind of is makes the base of building quantum computers. It is a method by which you can look into any noise model, you can but you can convert that into an average noise model which is stochastic Pauli in nature. This was called randomized compiling, or more famously it's called twirling. So the idea is, here you take a circuit. This circuit is affected by different kind of noise that we just discussed about. There is depolarizing noise, there is decoherence, there is over rotation. All of these kind of noise are here. Now what we want to do is, I want to sandwich this circuit in such a way that, so let's take an example. Let's take this example. Okay, forget this first gate, or let's take the first CNOT gate. I have put X and Z before the CNOT gate, right? I have put X and Z before the CNOT gate. It should be functionally equivalent. So if I put X and Z before this, I should put something after this, so that this taken together is functionally equivalent to the original single CNOT gate. I cannot change the functionality of the circuit. Now, if you already know this, great. If you don't know, just for the moment, trust me that if we and go back and try this out, it's easy to do. If we have an X gate on the control, it goes to both control and target. So if there is no Z gate, if you have the X gate and if you say that, okay, I'll put this after the CNOT gate, you have to put an X gate here and an X gate here. On the other hand, if you have a Z gate at the target, the same thing happens. If you want to say, I'll take the Z gate here, you have to put a Z here and a Z here. Only then they will be identical. And I would really urge you that go back and try this. This has many implications. It is easy to try. You just take some, say, alpha 0 plus beta 1 as your first qubit and say gamma 0 plus delta 1 as your second qubit, apply a CNOT gate, then see what happens, then apply X gate here and then a CNOT gate and CNOT gate and two X gates followed by here. So that way you can see that what I am saying, these are identical. Why is this important? First, this is twirling. We will go more into this. Why I am kind of emphasizing that please go back and just do this calculation if this is not immediately obvious to you. But this also forms the main basis of quantum error correction. The fact that if you take X gate and if you try to put it here, it will flow to both the control and the target. This is how error is detected in error correction. And similarly, if you take Z, it will flow to both control and target. This principle is the beginning of error correction in quantum. So if you just go back and try to do this, I'm sure you'll be able to relate. If not, we can talk more on this. But coming back to what we are interested in, so here, as I said, if you take X and if you put it across the CNOT gate, it will come both to control and target. Same, if you take Z in the target and you try to flow it, it will go to both control and target. So we have X and X, Z and Z together, they will form Y. What it means is a single CNOT gate versus this entire thing. These two are same. These two are functionally equivalent. So why am I doing this suddenly? This sandwiching kind of thing. Why am I doing this? The reason is that if you the reason is that if you kind of apply these gates randomly, so you can, I have put X and Z here, you can randomly select from the Pauli gates, put something here, calculate what should happen here. So this one is independent. You can put whatever Pauli gates you want here, but you have to calculate what gate should go here, so that the functional equivalence is maintained. Once you do that and once you repeat this many times and you take the average, irrespective of the noise model, the original noise which is affecting the system, which can be very complicated. I mean, I just talked about over rotation and depolarizing and decoherence. These are not the only types of noise, right? It is a general definition is it's a completely positive trace preserving map. It can be as general as this. But whatever it is, when you do this, this is called twirling. This this sandwiching the gate with Pauli's. These are called Pauli twirlings. So when you do this, and when you take the average many times, when you repeat this many times and take an average of them, the average noise model becomes stochastic Pauli. Now here comes the interesting thing, that my average noise is stochastic Pauli. That means I can do the extrapolation by the way we were doing, and the assumption that the noise model doesn't, the nature of the noise doesn't change, is preserved through Pauli twirling. So it is this important. The way you can do twirling in runtime is that if you just go to estimator options, you can import this from Qiskit IBM runtime and you will find twirling here. There are different strategies and you can see what the different strategies do here. I'll elaborate these, what the different strategies do, and then you can twirl the gates, you can twirl the measures. I'll come to how we can twirl measures. So let's not worry about this at this moment. And we can kind of define how many randomizations we want, how many shots we want per randomization. So for example, if for this one, you may want 100 shots. For another configuration, you may want another 100 shots. So you take 200 configurations, 100 shot for each. This is what it means. I mean, you can play around with this. The way these things do is this active account, as you can see, it kind of goes from the top and it does like this active circuit. Whenever any qubit is part of the circuit, it will twirl the entire circuit. Only active, it will only twirl this portion, and all it will all the qubits irrespective of whether it is part of a 2 qubit gate or not. These are different strategies and you can use anyone. There is no immediate way to say this is better, this is worse. So you can do any one that you want. Now, what happens here? See, one thing you will be obviously clear to you, there's this single qubit gates also have some noise. Well, they are much lesser than 2 qubit gates, like almost 100 times lesser than 2 qubit gates, but they are not zero. So when you start putting in these more gates, they will have some noise and the result will be slightly worse. This will happen. But what do we gain doing this? We are allowing slightly increased noise. What do we gain with this? So if you look into this circuit, this is once more a transverse field Ising model that has been executed. And if you just run the circuits, you see the ideal value is like this 0.8, and we are trying to get the expectation values of the ZIII, IZII. So single Z acting on each qubit, IIZII, single Z acting on each qubit. This is what we are trying to see how what happens when we do that. If you see, as the number of trotter steps increase, the depth of the circuit increases, the nature of the noise increases and things go bad, right? Definitely. But let's see here. Here the bare noise, so if there is no twirling, no mitigation also, this is just bare raw information, raw and with twirling, no mitigation. Here if you see, it is going down very nicely. It seems almost an exponential, the raw data, the red one, the raw data. Here if you see, it goes down something like this. It is not really exponential. Here you can very nicely see the periodic nature that I was talking about. Here the periodicity is slightly different. Here it is like this. So what is happening is, every time the nature of the noise is different. And if that happens, it becomes very difficult to deal with this kind of noise. How do you extrapolate? Right? If so, what extrapolation will work for this, the extrapolator that will work for this one will not work for this one. Whatever works for this one will not work for this one. So how do you really work on that? That is why twirling is so useful. If you see, when we do twirling, you can say that, okay, you see the results are getting worse. I mean, this is the ideal value and your bare results are better and your twirled results are actually worse. True, I agree that the twirled results are worse, and we argued why it will be worse, because these single qubit gates have some noise. These are not zero noise gates. But now if you see, all the natures of the noise are the same. They are all exponential. They are all exponential. And if you look into a small regime, you can say, no, this looks like linear. That's fine. We already discussed that you can do a Taylor series expansion and truncate and get a linear extrapolator. That is fine. Like if you say that this is linear, this is not exponential, that is totally fine. But the nature of the noise becomes similar for each of the cases. Now we can properly fit an extrapolator. If we go for a linear extrapolator, that will work for everything. So this is where twirling becomes very useful. Once more, what Qiskit does, see, I mean, I kind of told yesterday that we don't need to be very precise about what is error suppression and what is error mitigation. But in case any of you want to be precise, twirling is error suppression. It is not error mitigation. Why? Because we said in error suppression, you don't need any extra runtime. In error mitigation, you do. When we did zero noise extrapolation, we were running the same circuit many times. So we have to have more quantum overhead for that. On the other hand, in twirling, what is done is that, say you are going to run 1000 circuits. What you can do, you can create these 1000 instances. You don't need to have the same circuit 1000 times repeated. You can have this, say this is one instance. In the second instance, you have a different gates here. Third instance, you have different gates here. In fact, this is what it is doing. It is telling you how many randomizations you want, how many shots you want per randomization. So it gives you a lot of power. You can say that, okay, for each randomization, I want a single shot. Then if you have, say, this will be roughly 20,000 shots, then you can have 20,000 randomizations, or you can break down your number of randomizations and number of shots properly. What I mean to say here is you can use 20,000 shots either to run this original circuit or to run different variants of this twirled circuit. It can be 20,000 shot, 10,000 shot, whatever you choose as your N. Within that N, you can either run N identical circuits or you can run N twirled circuits. They are all functionally equivalent, but now you get N different results coming from the twirling and you can average. So this is why twirling is error suppression. It doesn't require any extra quantum overhead. In practice, once more, twirling is performed only over 2-qubit gates because single qubit gates are way less noisy than 2-qubit gates. And this is from one of my papers that I did, and you kind of saw this periodic nature coming through, but here I can show you with respect to zero noise extrapolation. This was again done for a circuit which is similar to this. It's called a MBL circuit, many body localization circuit. It's from, yeah, quantum physics kind of things. Here, if you see that as the number of 2-qubit depth increases, this green value is the ideal expectation value. If I just do a noisy execution, no error mitigation, then this black is what I get. And as you can see, initially it seems good, but then it slowly moves away from the actual result. If I do zero noise extrapolation without twirling, you see this purple is what I get. And you can actually see this periodic nature coming here. And I'm sure all of you, if I didn't show you this blue curve, you will say that ZNE is worse than, I would rather take this black curve than this purple curve. But the moment you do twirling, this blue curve is what we have, right? So this is why this twirling is a super duper important thing. It is used like unanimously in quantum computers. Almost twirling is everywhere. Here is a question for you all. You can answer over chat, or if you want, we can come back to this question later. So what I talked about, that when you twirl with respect to Pauli group, so these gates coming from Pauli group, this is called Pauli twirling. And when I do Pauli twirling, I get a average noise model becomes a stochastic Pauli noise model, this form. On the other hand, if I twirl over the Clifford group, so instead of choosing these gates from the Pauli group, if I choose these gates from the Clifford group, which is a slightly bigger group than Pauli, Pauli is a subgroup of Clifford, then if you take the average, it becomes a depolarizing noise model. As you can immediately understand, this is a way mathematically simpler noise model than this one. Compared to this is more complicated. But Clifford twirling, so twirling with respect to Clifford gates by padding Clifford gates is not done. Why not? I'm telling you that Clifford twirling will give you a more simplified noise model, which is always better to have, but Clifford twirling is not done in practice. Why so? I would say take some time to think and we can come back to this. We will come to this measurement error mitigation next. So we talked of gate error, and gate error we can deal with zero noise extrapolation. There are different kinds of gate errors, like if the error comes from these depolarizing or stochastic Pauli kind of channel, ZNE is good for that. But then we also have this decoherence, we also have over rotation. So what we do is we always twirl the circuit. When we twirl the circuit, what we get is a average become stochastic Pauli noise, and we can use GNE to work on that. But as we discussed before, this does not address the noise coming from measurement. We need to address this separately, the measurement error mitigation. So what is measurement noise? Measurement noise is basically a very classical type of noise. It is as simple as saying that I ask you, give me a bit, 0 or 1. You tell me 0, I write down 1. This is the error. This is the simple error, bit flip. Nothing else can happen in measurement. And this usually, even in classical information theory, this is represented by what is called a binary symmetric channel. So we have the outcomes 0 and 1 bits. The outcomes can be 0 and 1. So it is as if the measurement apparatus asks the quantum state, are you 0 or 1? And when the quantum state says that I am 0, with probability 1 minus p, it writes down 0. With probability p, it writes down 1. So it makes an error with probability p. Similarly, it asks the quantum state, are you 0 or 1? The quantum state says, I am 1. It writes down the correct answer with probability 1 minus p, and it writes down incorrect answer 0 with probability p. This is the binary symmetric channel. But quantum measurement is slightly more complicated than this. It is slightly more complicated than this one. What we haven't discussed too much about, I mean, we have, but we are seeing this for the mathematical notation for the first time, is this decoherence, the T1 error. What is T1 error? How do we understand that? I told you that T1 is when you put a qubit in a higher excited state, it spontaneously releases the energy and goes down to the ground state. So how you can do that? You prepare a qubit in 1, you leave it idle for some time t, and then you measure. You do this many times, you will sometimes get 1, sometimes get 0. The probability that you get 1 is exponentiation of this small t, that is the time, and capital T1, which is a hardware characteristics. So the higher the value of small t, faster in exponentially, the probability that you get the outcome 1 goes down to 0. So we have T1 error in quantum computers. Why is this important? If you go to this 127 qubit Eagle processor, some details of that, 1 qubit gate takes roughly 60 nanoseconds. 2 qubit gates, 533, almost 10 times of 1 qubit gate. Measurement, almost twice of 2 qubit gate. Right? It's twice of 2 qubit gates and like way higher, almost 20 times of single qubit gates. So if you think that by the time you are measuring, by the time you are doing the measurement, the system is sitting idle, that means it has a possibility of going from 1 to 0 spontaneously. What is the probability of that? The average T1 of Eagle processor is 267 microseconds. And if you calculate this exponentiation of this measurement time divided by the T1, you roughly get 0.99. So the probability that the system actually decays by the time measurement is going on is 0.01, which is not negligible. It is not negligible. Why is it not negligible? Let's look here. If you see the average error of single qubit gate is 0.03%. Let's call it 0.04, 0.038, 0.03%, right? So it's 0.0004 or something like that. The probability of 2 qubit gates is 2.8%. So it's 0.028. So the probability of 2 qubit error is 0.02 roughly. And here I am talking of 0.01. So it is roughly half of 2 qubit gate, way more than single qubit gate. Only the error that is coming from the T1 decay during measurement. Correct? So only the error that comes from that. I mean, we haven't yet considered the symmetric kind of error that we discussed. Measurement, as we understand now, is not only affected by this binary symmetric channel. So this is kind of the problem of measurement. It is kind of the problem that you are telling me 0, I am writing down 1. This is the major problem of measurement. But measurement is also affected by the time it takes to do the measurement, and it is affected by T1 error. So if the outcome actually is 1 is 0 and you write down 1, see, when you have 0, 0 doesn't decay anywhere. So 0, you told me 0, I write down 1, that is basically coming from this kind of error, the binary symmetric kind of error. I make some mistake. When you tell me, I make some mistake while writing down. So 0 to 1 is affected by that. But when the outcome is 1 and you write it 0, it can be because of two things. It can be because of this kind of error. You said 1, I wrote down 0, I make those mistakes. Or it can be that by the time the measurement happens, it sends a pulse and everything, the pulse returns, it detects what has happened. By the time it happens, 1 has actually collapsed to 0, or the way it has kind of evolved, the probability of 0 has become higher, therefore measurement, when you measured, it collapsed to 0, something like that. So it is this 1 to 0 is affected by two type of noise, this measurement noise and T1 noise. And therefore, of course, you can understand that this will be higher, the probability of this error will be higher than the probability of this error. It is no longer a symmetric channel, it is an asymmetric channel. Going from 0 to 0 and 0 to 1 versus going from 1 to 0 and going from 0 to 1, these two are not the same. These two are different. So it's not a binary symmetric channel, it's a binary asymmetric channel. The moment it becomes a binary asymmetric channel, dealing with this both mathematically and practically is very difficult because these two probabilities are not the same. This means that you probability of 1 given 0, that means it was originally 0 but you wrote it down as 1, and this is probability of 0 given 1, that is it was originally 1, you wrote it down 0, this is greater. And in general, if you go and see the hardware data, this is almost twice of this. So it's an asymmetric channel. Dealing with asymmetric channel even mathematically is difficult because this is a very simple noise model. But the moment you have an asymmetric noise model, you cannot represent that using a unitary operator. You have to go to all those Krauss operator notations and everything. So what we do next is something called measurement twirling. Again, the idea is very simple. If you remember what was twirling, we had a gate. I put some gate before that and some gate after that so that functionally nothing has changed. This was twirling, right? I was putting, say, an X gate before, and I would accordingly put some other gates here so that functionally they are the same. Now, the point is that how do I twirl in measurement? Say, if I put an X gate before measurement, what happens if the outcome was supposed to be 0, it will become 1, right? Forget about measurement error for the time being. Let's say there is no measurement error. I forcefully put X here. So if my outcome was supposed to be 0, it will become 1 because I have put an X gate here. I need to account for that. How do I account for that? I'll keep a track that, oh, I have forcefully changed the outcome here. I need to return it back to its original state. And that we can do classically by putting a NOT gate, or rather just, I mean, this is a notation that you can classically put a NOT gate after measurement, or you can just write down in paper that, oh, you know, if the outcome was 1, I'll call it 0. If the outcome was 0, I'll call it 1, like this. So the moment we go for twirling, it will be that when you measure, say you are taking 1000 shots. So you have 1000 circuits created and measured. And we will randomly insert identity gate, that is do nothing, or X gate before measurement. And we keep track when we are putting identity, when we are putting X. And when we put X, we have to classically take account for that and make the correction. This is measurement twirling. Now what happens, you can actually, even without going to very complicated mathematics, you can understand this very very simply. What will happen here, say it was the original outcome was 1, and we know that 1 to 0 has a very high probability. But say you are measuring this 1,000 times, and sometimes, say with 500 times you put x gate before, so your 1 becomes 0. Now when your 1 becomes 0 after you forcefully put x gate, how will this measurement error act on that? Well, 0 can still become 1, but 0 becoming 1 because of t1 error, that cannot happen, because t1 error takes a 1 to 0, not the other way, right? So say half of the time you put an x gate, that means 1 is becoming 0 and it is no longer um, affected by t1 noise. That is one part. The other part is, say the outcome was actually supposed to be 0, so it wouldn't have been affected by t1 noise, but half of the time you randomly put x gate and you take that 0 to 1. Now it is affected both by the measurement error and by t1 noise. So half of the time you are making that your 1 is half of the time affected by t1 noise, half of the time it is not. Similarly, by doing this, you are making it that 0 is also half of the time not affected by t1 noise, half of the time it is affected by t1 noise. When you take an average of this, the asymmetry in the system goes away. The system becomes symmetric. So this is why measurement twirling is super useful. Like we will see the measurement error mitigation after this, but even if you don't do a measurement error mitigation, you see this is not requiring any extra quantum overhead. If you have 1,000 shots, you will randomly select 500 of them and put X gate. This is only what you will do. There is no extra quantum overhead here. So doing measurement twirling is always very good. It removes the asymmetry of the system. So here is another question. If you want, we can discuss this later. Is previously when I was doing gate twirling, I was putting in X gate, Y gate, Z gate, every type of gate. Here I am saying that I will only put in X gate and I gate. Sometimes I put only identity, that means I don't do anything. Sometimes I put X gate. Why? Why don't we put Z gate and Y gate also? What will happen if I say that no, Y only I and X? I will put all the Pauli gates, I, X, Y, Z. What will happen if I do that? Think, I mean, you can just think of that. But using measurement twirling, we can do a beautiful thing, which is this error mitigation for measurement error. And it has a beautiful name. It's called twirl readout error extinction. And in short, it is called TREX. The idea is, first, you just twirl the circuit. Okay. You twirl the circuit and you don't even take the original circuit. You just twirl the measurement. When there is no circuit here, you prepare the system, you twirl the measurement. This is what you do for a few times. Now, see, if there were no error in the system, if there was no measurement error, what should have happened? You start with 0, you measure, you should have, if you measured this 1,000 times, you should always get 0. 1,000 times you should get 0. Don't get involved in this mathematical notation, just follow what I am saying here. You start with 0. If there is no measurement noise, twirling is functionally equivalent, right? I am just flipping the gates before measurement and then classically doing the correction for that after measurement. So it is actually not doing anything new. I start with 0, I should always get 0 if there is no noise. But if there is noise, then the system will get a bit I mean, the system will sometimes give you 0, sometimes give you 1, because there is noise in the system, right? What we do is we calculate a function out of that. So whenever, remember once more, it is useful, error mitigation is only useful for expectation value. We spend a lot of time talking of this. So error mitigation is only useful for expectation value. Once you do the measurement, I will calculate some expectation value next. What will happen to your expectation value when there is measurement error? It will get scaled somewhat. What I mean that say your measurement value should have been 1. Ideal expectation value should have been 1. But because of measurement error, it can become something like say 1 by 6 or something. So there is a scaling. If you know this 1 by 6 scaling, then you can do the correction. And this is precisely what it tries to do. In general, when you have an original circuit, you don't know the actual expectation value. You are not expected to know. For small circuits, you can know, but then why are you running small circuits? You don't need a quantum computer to run small circuits. You ideally want to go to a regime where the ideal expectation value is not known. You cannot simulate the circuit. That is where you want your quantum circuit to run and give you reliable results. So the problem is that if I don't know the ideal value, how do I know how much got scaled? How much? So I said that if the ideal value is 1 and I have getting 1 over 6 as my expectation value, the scaling factor is 1 over 6. If the ideal value is 2 and I am getting say 1.5, I can calculate the scaling factor from there. 2 divided by 1 on 5, 1.5 or something like that. But I need that ideal value to calculate the scaling factor. That is why you start with an empty circuit. Because if you start with an empty circuit, it's just all zero. Your ideal value is very easy to calculate, irrespective of the number of qubits you have, right? And if you take Z-type observables, what will happen? It will be always plus one, ideally, ideally. And the moment you move away from there, so what this is doing is this is essentially just calculating all the expectation values and taking an average, noisy expectation value. This tells me how much I have scaled away from the ideal value. So that is why just running this empty circuit is important, because this gives you a baseline value. Next, we come to, this is called calibration. This is just an example, so don't take this too seriously. If there is no spam error, then this gives me 1. So there is no scaling. If there is no spam error, I start with 0, 0. My expectation value should have been plus 1. I get plus 1. If there is spam error, say I have taken 6 shots and I get something like this. I get the correct outcome 4 times and 2 incorrect outcomes. And if you calculate this, I get 1 over third, 1 by 3. This is the scaling factor. So this gives me the baseline. It is easy to calculate. This gives me the scaling factor. Now I do the same thing on the original circuit. U is my original circuit. So I do the same thing on the original circuit. What will happen? The original circuit will be affected by measurement error. I am not going to worry about gate error at this moment. Let's assume there is no gate error in the system. So the only thing that is affecting this thing is the measurement error. So, but I don't know the ideal value, ideal expectation value, because this is in general a very big circuit. I don't need to know the ideal expectation value because I calculated the scaling factor from this empty circuit. I'll take the scaling factor. I will calculate the expectation value of this circuit, the noisy expectation value here. I will calculate the noisy expectation value and I will divide it with the scaling factor. If you see, this is kind of the same thing. This is the exact same thing. 1 over n minus 1 inner product of s and x minus 1 over n minus 1 inner product of s and x. This is done on the original circuit, and this d0s is the notation when the circuit is empty. And then you just divide both of them. What I showed here, you can argue that, oh, you have taken these outcomes in such a way that you are showing that it is retrieving the perfect value. True. But if you use this T-Rex on a quantum computer, roughly it does better than doing away with 98% of spam error. So this is very powerful, very good, and as you can understand, very, very simple. Like you can yourself implement this very easily. But this deals away with measurement error. So we understood how to deal with gate errors separately, how to use twirling for gate errors, and then how we can use twirling that leads to stretch, the stretching factor, or however you call it, the stretching factor here, that allows you to correct for measurement error. So when you put all of these things together, how does the pipeline goes? First, you transpile your circuit. Now you need to amplify the noise. Gate folding, PEA, whatever, you amplify the noise. Now you need to calibrate the readout. So calibration is this. Calibration is this, just running the empty circuit and calculating this function. This is calibration. So you calibrate the readouts. Next, you twirl the gates. Now we have to twirl the gates and now execute. Once we execute, we have to take an aggregation of the twirls. That will give me an average noise model of stochastic Pauli. Now we calculate the expectation value on this aggregate twirl so that I can say that the noise which affects my expectation value is stochastic Pauli. Now I mitigate my readouts. How? By doing this, by calculating this outcome, and we already have the scaling factor from here, calibrate readouts, and we can calculate this. And finally, we do the extrapolation. This is the entire pipeline that needs to go. After transpiling the circuit, we first amplify the noise by doing some folding. Now we calibrate the readouts to find the scaling factor. Next, we twirl the gates. Then we execute. Then we take the twirl together and create an average, which will create the noise as to be stochastic Pauli. Then we calculate the expectation value over the stochastic Pauli noise model. We mitigate for readouts, and finally we do zero noise extrapolation, the extrapolation part. Of course, you can say, oh wow, that was a lot of things. I mean, you talked of so many things, and if all of these things I have to keep in mind when running my quantum circuit, that is pretty tough. So of course, Qiskit has your back. You don't need to do everything manually that we just talked about. If you go to Qiskit IBM runtime, you will see there are resilience levels, and the default is 0. Sorry, default is 1, but you can put a resilience level 0 where there will be no mitigation. So you can get the raw value, unmitigated value. The um, default value is 1, where you just do twirl readout error extinction T-Rex along with gate twirling. And finally, if you go to 2, it will give you zero noise extrapolation together with gate twirling and T-Rex. So if you go to 2, it is doing this entire pipeline. You may want to do some part of it. So if you put it 1, it will just do measurement error mitigation, not ZNE. If you put it 0, it will not do any mitigation. You can ask, what if I want to do ZNE? I don't want measurement error mitigation. Maybe for a problem you want to understand that how my measurement noise is hampering different things. So I mitigate for gate noise, but I let measurement noise be there. That will not come from resilience level, but you can actually go and turn things on and off. You can turn things on and off, and you can show how to you can actually say that, okay, I'll use ZNE, I won't use T-Rex. All of these are here, and I plan to show you one small notebook on this. But yeah, maybe we can stop here for a small break and come back with this building confidence thing. Okay, there are some questions, I guess. One of the questions is, increasing folding will increase ZNE. I don't understand what you mean by that. I mean, ZNE is that when you do folding, you calculate expectation values and then you extrapolate to get a zero noise estimate. This entire thing is ZNE. So I'm not sure what you mean that you want to mitigate ZNE and PEA as well. Let's see if I can share this screen. I don't know if this will be shared. Okay. Yeah. So yes, so this was the question I was talking of, that yeah, I mean, ZNE is not just folding. ZNE is the entire thing together. You fold, you calculate expectation values at different levels of folding, and then you extrapolate to get a zero noise estimate. This entire thing is ZNE, or this entire thing is PEA. You don't you don't need to mitigate for that. These are themselves mitigations. Yeah, I think we answered this. This was kind of 0, 0, 0 and all 1, 1, 1. These were the ideal outcomes, and the values here were just taken randomly. Yeah, this is a very good question, that what is the importance of shots for ZNE? Strictly speaking, the more shots you take, the lesser will be the variance. But yeah, I mean, you can do a calculation of how much precision you want, and you can calculate how many shots are required for that. I think it goes as 1 over square root of n or something like that. But in general, yes, I mean, the more shots you take, the better it is. I mean, it will be more accurate to calculate the expectation value, and of course it will be better. I have exactly forgotten the scaling, but I think that higher the shots that you take, the imprecision goes down as 1 over square root of n or something like that. Okay, so here is one question: what is the difference between applying noise model based on quantum gates? Yeah, this is something again we discussed yesterday. When you do this Lindbladian master equation, that is the PEA. That is how you learn the noise in the system. The first thing it assumes is that you have, so the total noise can be 4 to the power n cross 4 to the power n. That is the CPTP map size. The first thing it will say is that you have twirled the systems. So now it becomes a stochastic Pauli, and it will have only 4 to the power n degrees of freedom. The next, it makes an assumption that noise is only nearest neighbor. You can ask that whether this is a good assumption. This is a good assumption. This is not a perfect assumption, but this is sufficiently good assumption. Under this assumption, you do a tomography. So when you do that tomography, now it becomes doable because you have already made two layers of simplification. Now it becomes doable, and usually PEA is better than ZNE by that. Okay, great. Yeah, so if there are no more questions, maybe we can take a small break and come back.
Sure, sir. So, means we will resume the session from what date?
5 minutes break.
Okay, okay, sure, sir. Okay.
Yeah, let's start around 4, 7 or something.
Sure, sir.
Okay. Should we start?
Sir, if you are ready, we may start. As participants are still there, so we may start,
Okay.
sir.
Okay. Sure. Yeah. Let's get started with something which is usually not discussed a lot. But this is something which is very important. Um, you will realize this. The reason I wanted to bring it up here is most of you have been doing quantum computing, these FDPs and everything for quite some time now, and you are no longer really novices. So, I mean, you have some grasp of this topic, and therefore this is a slightly advanced material that I'm going to talk about now, but you will soon understand this is something which is very important and which is very useful. I'm not sure how many of you have run this ZNE or something. If you don't run, immediately it becomes a bit difficult to appreciate it in the beginning. But I encourage you to please go and run this ZNE on the few minutes that you have. And you will immediately realize when you run ZNE how important this part is, building confidence. Where is the question? So I told you that if you have, say, uh, noise factors, we were talking of 135. You repeat the gates 3 times, you repeat the gates 5 times, and so on. And then I told you that if you have pretty deep circuit, then you cannot go for this, say, 5, because then your um, folded circuit's depth becomes very big and everything. The question is, what do you mean by deep circuit? Can you quantify what do you mean by deep? No. The answer is no. The second thing that you will say that, oh, you said 1, 1.2, 1.4. This is what you were discussing when you were doing partial folding. I'll take 2 out of 10 gates. What if I take 1, 1.1, 1.2? Is that good, or I don't know? I mean, all the answers here will be I don't know. So therefore, the question now is that, say you end up using some noise factor which is not good for a particular circuit. Your extrapolated result will be completely away from the ideal result. But when you go to bigger circuits, when we talk about running things at 100 qubits, right? If you don't know, if the answers are here that I don't know, how will you choose a noise factor? I don't know what do you mean by deep, I cannot quantify a metric for deep, and then I say you run things on 100 qubits where ideal result is not available. How do you know that your result is correct? How do you have the confidence that I have used error mitigation properly and the result that I see is actually correct or good enough? Like, it's not something totally away. How do I know that? So this is where I want to go into this building confidence. And what we have in from IBM Qiskit is a set of debugging tools. And you will see this is something very simple. All these are, let's avoid all these things. The question is that if you have a small circuit, you would ideally want that let's just use a simulator and run it, because then there is no noise. Then the question that, oh, is the answer correct? Is it good enough? All these questions don't come if you just if you can use a local simulator, right? If you use something like this. But this is feasible only for small circuits. What happens when you go to much bigger circuits? This thing that I'm telling you, 100 qubit regime, how do you reach there and still have confidence? That's why we have what is called NEAT. This is Noisy Estimation Analyzer Tool, the full form, and it's a very neat name. The name is neat, right? So the idea behind NEAT, as you will see soon, is very simple. And the idea actually is very, very related to the T-Rex mitigation that we saw. What was the idea of T-Rex mitigation? You want to know the scaling factor. To know the scaling factor, you need to have a baseline result. How can you have a baseline result? You can have a baseline result if you um, know the outcome. How do you know the outcome? Let's take a normal circuit where you start with 0 and you just measure and you calculate the scaling factor from here, because for this circuit it is easy to calculate the outcome. The same structure we will go here, that see, if you just use a small circuit and if you use a ZNE on that, you can say that, oh, this is my ideal result, this is the result that I got by using ZNE. I use this kind of noise factors for ZNE. Maybe this is close enough to the ideal outcome. That means my noise factor and everything was good. Or if it is far away from the ideal outcome, my choice of noise factor and everything was not good, right? How do I get that baseline when I go to much larger circuit? So this is where NEAT comes into play and the idea of Cliffordization comes into play. You know, I am sure that Clifford circuits are easy to simulate. So we can simulate much bigger Clifford circuits. In general, we can simulate up to 32 qubit general quantum circuit. But if it is a Clifford circuit, we can easily go to 200, 100 or even more bigger. So if it is a Clifford circuit, we could have just simulated it, but not every circuit is Clifford. But what we say here is that we start with the input pubs. I hope you all have seen Qiskit, and pub is the data structure that is used to run jobs, primitive unified blocks. This is the data structure which is used to run quantum circuits. In general, the circuits in the pubs are non-Clifford. I mean, there is no reason why you only have to run Clifford circuits. And if you only have to run Clifford circuits, you should rather use a simulator, not a quantum computer. Now I convert these circuits into Clifford. And in the next slide or the slide after, we will see how to do that and what are the perks of doing that. But we convert these circuits into Cliffords. Now, see, these are the non-Clifford gates that we have. Sorry, these are all the set of gates that we have in our quantum computer. SX, RZ, these three are common. CX was previously in the Falcon processor, ECR in the Eagle processor, CZ now in the Heron processor. These three are the 2-qubit gates. It differed from processor to processor. If you look into all of these gates, X is a Clifford gate, SX is a Clifford gate, C0, ECR, CZ, they are Clifford gates. Only RZ is the non-Clifford gate. Even then, if your RZ angle theta is in this, any one of these four, it will become a Clifford gate. But if you put an arbitrary angle theta, it becomes a non-Clifford gate. So when you create your circuit, when you decompose your circuit using the basis gate set, the only non-Clifford gate that we encounter are these RZ gates. This is something, this, just keep this in mind, this will come very handy in the next slide. Now, the moment we convert this into Clifford, we can get the ideal result and we can get the noisy result from there. And now we can build a confidence. This noisy result you can just run on backend and you can get a result. And now you have a baseline. Now you can compare that, oh, okay, my result is close to the ideal outcome, or my result is not close, it is quite away from the ideal outcome. The computation was not good. Now, this doesn't give you the entire story. We need a few more things to understand the entire story. First is why is NEAT expected to work? When you have a Clifford, non-Clifford circuit, I'm telling you that you convert it into Clifford and then you take a baseline based on that, you take some results based on that, and this is sufficient to give you confidence about your original non-Clifford circuit. The confidence that you gain from the Clifford circuit is sufficient to gain confidence for the non-Clifford circuit. Am I telling this? I mean, why does this hold? Why is this expected to work? The reason is, remember, let's come back here. RZ is the only non-Clifford gate. that we have. So let's say this is an original circuit, and this circuit is, as you can see, in general non-Clifford. We have some very random rotations in RZ. We have some very random rotations. The first thing it does is it change. Remember, everything else is Clifford. So if I Cliffordize this circuit, what it means is I will take this angle, I will convert it into the nearest multiple of pi by 2. This is what I'll do. I'll take this angle, whatever angle this is, I'll convert it to the nearest multiple of pi by 2, integer multiple of pi by 2. So here, as you can see, the nearest multiple was minus pi by 2. This one was 1.45. The nearest multiple was pi by 2. So these kind of things, when you do this conversion, now this circuit is Clifford, but the point here is, see, how does noise affect? Noise affects the gates. All the gates are same here, only the rotation is different. And RZ gate is directly not applied in a quantum computer. This is kind of the rotation in the rotation is actually kept track of. It's essentially just a rotation of the reference frame that is kept track of in software. So but even then, all the gates are the same. The structure of the circuit is the same. Whenever the circuit was remaining idle, for whatever time it was remaining idle, it remains idle for the same time. All the gates are same, just some angles have changed. So the way noise will act on this circuit is expected to be very similar to the way it will act on the original circuit. This is the reason that Cliffordization is expected to work. Whatever you can say in terms of noise, whatever you can say in terms of this Clifford circuit will hold for this non-Clifford circuit, or will hold pretty well. I mean, not maybe one to one, but sufficiently well. So the workflow is very simple. You Clifford the pub, you have some noise model, you do a noiseless simulation. Since you make the circuit Clifford, you can do very large noiseless ideal simulation. You have the baseline. If you want, you can do a noisy simulation, and then you run the Clifford pubs on the QPU, maybe with error mitigation, without error mitigation. Now you can compare your result with the noiseless simulation, and you can see whether it's good or not. And depending on this information, you build a confidence that, okay, the error mitigation that I am using is good. This confidence, once you build on the Clifford pub, you can use that error mitigation parameters to go and submit the actual job to Qiskit. And this is the neat API. Yeah, these things are not important. Let's go and see a code and see this working actually. Let me do that. Yeah. Is this font okay, or maybe I can just make it slightly bigger? So here I have just
Maybe a little bit zooming in will be better, sir.
better now.
Yes, sir. Now it is clear,
Okay,
sir.
great. So I have already from Qiskit IBM runtime, I have already imported my Qiskit runtime service, and we have this estimator batch and everything. Let's run from here. I'll generate a quantum circuit, and what I want to show you, I mean, don't get a wrong message out of this. I will take a 30 qubit circuit. And the reason I will take a 30 qubit circuit is I want to show you, because at 30 qubit, we can actually get the ideal outcome even for the original circuit. What I want to show you is that when you do this analysis with Clifford circuits and you take that result back to the original circuit, it actually holds. What I just said actually holds. That's why I'm taking a smaller circuit to just show you that it is holding, it is doing what it's supposed to do. So I'm taking this 30 qubit. My observable is of this form. It's a single Z on each qubit and an average over all of this. This is a very common observable that we often take. Of course, there are observables which are problem specific, like if you have a optimization problem, or if you have say chemistry problem, the problems will have their own observables. But in general, this is a very good observable to try things out if you are doing it yourself. The reason is that this is weight 1 observable. See, higher the weight of the observable, more is the effect of noise. The noise affects exponentially. So usually we take low weight observables to check that things are happening correctly. And now if your problem requires high weight observables, then it does. Like many chemistry problems require very high weight observables. And taking an average is important because if you just take Z on a single qubit, say that particular qubit is very good and you get a great result. That doesn't tell you the whole story. Or if that particular qubit is bad, it gives you a very bad result. That also doesn't tell you the whole story. So that's why we usually take an average over all the qubits so that you kind of get the entire story of what is going on. So this is my observable. As you can see, it's like Z on each qubit and with equal probability. I create a Hamiltonian simulation circuit. The circuit here is not very important. Let me run the simulation and then talk, because it's 30 qubit, it will take some time. So this is a Hamiltonian simulation circuit. The way I have taken this circuit is that it is a very hardware friendly circuit. Um, and it is very easy to now create this XYZ Hamiltonians. If you are doing physics problems, it is very, very simple to create these Hamiltonians. The Hamiltonian in general will have a form where you will have XX, YY, and ZZ terms, and these are the coupling terms, and these are the corresponding constants. So in general, it is like, it looks something like, say, it is something like JXX plus JYY plus JZZ. This JXX, JYY, these are the coupling constants, and these are the values that we have selected. Here you can select any other value. There is nothing very special about this value. And this is how, when two nearest neighbor sites interact, the strength of interaction is given by these values, the JXX and everything. And then each qubit is also, or each site itself has its own potential magnetic field and everything. So you can have something like HXX plus HYY plus HZZ, things like this. Hx, Hy, Hz, these are the external magnetic fields, and I have taken values like this. Once more, there is nothing very special about these values. You can take any value that you want. This is the Hamiltonian, and this is Hamiltonian evolution of Hamiltonian system that we are looking at. This is Hamiltonian simulation circuit. So I want to evolve this Hamiltonian. That means if this is H, what I want to do eventually is e to the power minus ITH. I want to do this kind of evolution. And here you don't have to create circuit for this separately. You can just call this generate time evolution circuit. You know that you have to do some trotterization of this. So you can put in the Hamiltonian, the H, the time, small t, and the type of trotterization you want. Here I have used Lee trotter. There are other methods like Suzuki trotter. You can choose the number of trotter steps. You can do all of those and it will just create the circuit for us. And here, as you can see, it has created the circuit for us. It's a very hardware friendly circuit. I have chosen this air simulator, and I'm creating this estimator V2 mode equal to air simulator. We talked of pub. A pub is in general a tuple. Maybe you all know this, but just for the sake of tuple, observable, and parameters. This is what a pub is, and we pass in a list of pubs. This is not a parameterized circuit. All the parameters are already well defined. And as you can see, this is not a Clifford circuit. We have very different RZ parameters and all. So here I am putting in my pub, which is my circuit and my observable. And I have used this to run on an ideal simulator. And I have my original result here. So my ideal simulator result is 0.87, roughly, the expectation value. Now the question is that when I want to run this on a real quantum computer, I want to do zero noise extrapolation. What are the noise factors that I should use? What is the extrapolator that I should use? Will you say this circuit is deep or sufficiently deep? Why we take rotation XYZ kit? Okay, let me come back. I'm not very clear what you mean there. Let me come back after doing this. So all these questions that we were asking, is 135 a good noise factor, or is it like sufficiently deep? We need to go to partial folding. I said if your size is small enough, you can go for linear. If it is slightly big, you go for quadratic extrapolator. Is this small enough? Is this slightly big? All these questions, these are some heuristic terms that I used. These are not mathematically quantified, right? So here is where we will use this. So first I am going to transpile my circuit. So I can import the generate preset pass manager, and just using optimization level 3, I'm transpiling my circuit. I have transpiled and I have created my pub, which is like the transpiled circuit here. Now what I will do is from this Qiskit IBM runtime dot debug tools, I will import neat. So if you are using the latest version of Qiskit runtime, you will have neat there. I can just put in the backend to neat, just calling it analyzer because I want to analyze things with it. And here I am putting this ISA HS circuit. This was my original circuit. And here, if you see, I don't know how to make this bigger. We still have some RZ rotations which are not in multiples of pi by 2, integer multiples of pi by 2. But now if I just call analyzer, which was this neat, if I just call to Clifford here, I can convert it into Clifford pubs. And if I draw the picture of that, you will see this is minus pi. Previously it was minus 9 pi by 10, and it has been taken into the nearest multiple of pi by 2, minus pi, and so on. So all the uh, rotations here has been changed to nearest multiples of pi by 2. Everything else remains the same because everything else is Clifford here. There is nothing non-Clifford in those things. Now, see, I already have Clifford circuit. I can get the ideal outcome for the Clifford circuit. I just call analyzer.ideal sim. I put in the Clifford pubs, just putting in a seed simulator if you want. If you don't want, it's totally fine. You see, the ideal result of Clifford is 1. So here is a very interesting thing because this is what I wanted to highlight properly. This was a 30 qubit circuit, so I could calculate the ideal expectation value of the original circuit, which was 0.87. This is 1. So the expectation values are not supposed to be the same. They cannot be the same. This circuit and this circuit are different. What the only argument that I am making is that the structure of the original circuit and the Clifford circuit, they are same. Therefore, the effect of noise on them will be the same. Okay. So I have got the baseline result by running the Clifford circuit. Now, okay, so this is a good example of seeing how we should be running circuits. There are 3 modes to run circuit. The job mode, you can just run a single job. There is a session mode used for VQE and everything, which is unless you are doing variational algorithms, it is not preferred. If you do session mode, the moment you start your calculation till the moment you end it, irrespective of whether you are using classical resource or quantum resource, you will be charged for the quantum resource. So not always kind of good thing to do, a good choice. not a good recommendation. Batch is a very good thing to try. What batch mode does is that if you already have a set of jobs that you want to run, if you already have a set of circuits that you want to run, you can pack them as a batch and you can upload them. What happens is that when you upload them, there is no guarantee that the jobs will run one after another. In general, in session, there is a guarantee that it will run one after another. But batch tries to maintain that. It usually tries to maintain that your jobs should run together without any giving you any guarantee. So I create my estimator. I have just taken 6,000 shots here. No particular reason of taking 6,000 shots. I am putting resilience level to 0. Remember, 0 meant no mitigation, 1 meant T-Rex, 2 meant ZNE plus T-Rex. Now, I am individually putting in, this is what I was saying, that is why I could have just done resilience level equal to 1, but I just also wanted to show you how you can manually turn on things and turn off things. So here I am adding readout error mitigation. So what I can do is just say resilience dot measure mitigation equal to true, or you could have just said resilience level equal to 1. But this one shows you how you can manually turn the for different knobs here. Next, I want to add gate twirling. So I am doing twirling dot enable gates equal to true. Num randomization I have put to auto. So how many randomization it want? I think by default it's 32. Now I am putting my ZNE mitigation equal to true, and the extrapolator that it will try are exponential and linear. It will try two extrapolator. I am coming up with 4 noise factors. You can take more. I mean, if you ask why 4, there is no reason why 4. I mean, I'm just trying to show you a proof of concept here. So nothing more than that. I have taken these 4 noise factors to try and these 2 extrapolators to try for each case. And I will see which one does the best for the Clifford circuit. I also turn on dynamical decoupling here. I'm not going to run this live, because if I run this live, the way you go into queues, I will also go into queue and then we will be sitting awkwardly. So I ran this before. These are the job IDs. For that, I will retrieve the jobs from here. So here, as you can see, I can just use service.jobs, give my job IDs and retrieve the jobs, and then I can retrieve all the results from here. This is to calculate the relative error. In the Clifford circuit, I already have the ideal outcome, which was 1. If you remember, it was 1. And I am experimentally going to find some outcome. Experimentally, I am going to use different noise factors and find some outcome corresponding to this. I am going to turn on, turn off dynamical decoupling and everything. So for each of those cases, for each of these noise factors, say 135, I am going to see how close this is to the ideal expectation value, how far it is. Like, is this closer to the ideal expectation value, or is this closer to the ideal expectation value? This is what we are finding here, the relative error of the ideal versus the experimental for each experimental setting. Now if you see, what I am doing is relative error. I'm just calling this the Clifford ideal result versus jobs I dot result. So I have many jobs. I have here 8 jobs, and for each of the job I am putting in the expectation value and the ideal expectation value, and it will calculate the relative error for each of the case. Yes, let it do. It is just extracting the results and everything done. So you see, I have all the relative errors. There are 8 cases. Why 8 cases? Because I have 4 noise factors here. First, I haven't used um, dynamical decoupling. Then I have repeated the same thing using dynamical decoupling. So although we didn't discuss dynamical decoupling, if your system is sitting idle for a long time, then dynamical decoupling kind of tries to reduce the effect of T1 error. If you look into this circuit, of course, there are certain cases like here the system is sitting idle for a long time. But in most of the case, if you think, it's a pretty dense circuit. The circuit is not sitting idle for a long time. So here, if you try to do dynamical decoupling, it is going to have an adverse effect. And that is what we see. First, we try without dynamical decoupling, then with dynamical decoupling. So this first four, no dynamical decoupling, next four, dynamical decoupling, and this four noise factors. Here you see when I have used dynamical decoupling, the results are pretty bad. On the other hand, these are the first four cases without dynamical decoupling. This one has the lowest relative error. Which one is this? The second one. So that means 1, 2, 3. What it tells me is that for the Clifford circuit that I have, if I use 1, 2, 3 as my noise factor, this is giving me the best result. Out of all these four, you could have chosen many more and tried many more. But out of this four, the 1, 2, 3 without dynamical decoupling is giving me the best result for the Clifford circuit. Now we will come to the other part that we said is that since the structure of the circuit remains the same, whatever holds for this Clifford circuit will hold for this original circuit. The way noise affects the Clifford circuit and the original circuit are very similar. This was our heuristic, right? This was our assumption to begin with. And we have obtained from the Clifford circuit that 1, 2, 3 is the best thing to go for. So now I am going to again start with everything that I do. See, I have done the same thing here. I have taken an estimator. I don't need to try many things now. So I'll just run a single circuit. So this is a job mode here, not a batch mode anymore. I am putting in measurement error mitigation, twirling, and then in ZNE mitigation, I am no longer trying out different things. I have just put that 1, 2, 3 is going to be my noise factor. So once more, my final job ID is this. So I'll take this. This is done on the original circuit, the original Hamiltonian simulation circuit. And I get the EXP val HS. You see, I get a very good result. 0.87 was the original result. If you remember, let's go back. 0.87 was the original result. I get roughly 0.86 almost. And if we just plot this, see, we have very good result from experimental by doing this zero noise extrapolation, right? And this is the building confidence part, that when we say that you need to go to 100 qubits or those regimes, how do you know that you are doing your error mitigation well? This is how you do it. Use the neat tool. You have to try out a few things. True, you have to try out different noise factors, but do it on a Clifford circuit. Make the heuristic that whatever the way noise works on this circuit is equal to the, not exactly equal, but equivalent to the way it works on the original circuit. So whatever setting is best for the Clifford circuit is also best for the original circuit, and we show the result that it works actually. So yeah, so this is what I wanted to show here. So we'll stop, and I think there are already a few questions, and if there are more, we can take those questions. Yeah, there was one question why we take rotation XYZ gate. It's the way the Hamiltonian simulation is created with RX, RY, RZ gate. I mean, that's just a way of creating the circuit. But yeah, if there are more questions, we can take those. Okay, what we observe from the bar chart. Yes, so what we observe, it's the same thing that we observed uh, from the exact result, that this is the ideal expectation value. The blue one is the ideal expectation value. and the purple one is the experimental expectation value. So the ideal, the result also, we found that the ideal expectation value was 0.87, and the experimental expectation value by finding out the best noise factors is 0.86 roughly. So what we understand from here is just a pictorial representation of this number, that the result of the original's ideal outcome and the experimental outcome by doing ZNE using NEAT is actually doing very well. Like, it is giving me a result which is very close to the original result. This is what we get from here.
So I think there's no more questions, sir. So participants, I again request you all, if you have any question or doubt you want to discuss, just put it in the chat box. Otherwise, we will basically close the session for the day. So one more question is there.
Okay. What happens if X, Y, and Z are grouped? I'm not sure I understand this question. If you can elaborate this question, or if you can just maybe unmute and say the question, that will be great. The second question that we have is, can we rerun it until we reach the ideal value? Yes. So we can rerun things. I only tried out 4 settings, or rather 8 settings, 4 different noise factors with and without dynamical decoupling. You can choose to actually you can actually choose to try out many other things and see which one gives you the best result. But given the outcome is a floating point number, maybe getting the exact result is very difficult, but you can always set a threshold and say that this is what we obtained. I'm good enough if you obtain something better than the threshold. That is doable. Difference between error mitigation and suppression. Strictly speaking, there is no mathematical definition that this is mitigation, this is suppression. What we say in general is that if you have things like if you have, say, some protocol um, where you need to run multiple quantum circuits, then it is mitigation because it has an extra quantum overhead. And if you don't need to run any extra quantum circuit than your original circuit runs, then that is what we call as suppression. This is just a very like naive way of differentiating, and there is no mathematical difference here. How to validate value of CNE? I mean, that's what we discussed with NEAT right now, how we can validate the value of CNE. Um, you can just take a Clifford circuit and you get the ideal outcome of the Clifford circuit. You try out different settings of ZNE and you see which one gives you the best result. And since you have the benchmark, the ideal value in terms of Clifford circuit, you can validate that your ZNE is doing fine. And then you take that setting and you run it on the original circuit that you are interested in. What if Pauli X, Pauli Y, and Pauli Z grouped? I'm still not sure I get this. What do you mean by grouping these things? So X, Y, Z are 3 Pauli gates. And yes, I mean, if you have X, Y sitting together, sitting one after another, you can combine them. It will become a Z gate. These things you can group. I mean, if you have multiple Pauli gates sitting one after another, you can actually combine them into a single Pauli gate, if that is what you are asking. Um, how to analyze the output of a program. I mean, I'm not very sure. Again, I follow this. We just saw with NEAT how you can analyze the output of a program, how you can verify that the output is correct, because you have the ideal outcome, you have the noisy outcome, and you can validate or you can verify that your outcome is becoming closer to your ideal outcome, and you try out different settings and you find out which setting is doing the best. The bar chart is nothing very critical. It just figuratively shows that your experimental value is close to your ideal value. That's all. I mean, nothing more in the bar chart here. Is it dependent on the current condition on the of the processor? Is what dependent on the current condition of the processor? Yes, I mean, see, I mean, if you just run the same circuit again and again, you cannot expect to get very different outcome. It will be slightly different, but you cannot expect to get very different outcome coming out of there. The way the processors are, the way the noise are, if you run the circuit again and again, you will get outcomes within some bounds, of course, not beyond that. Like, this will not happen that if you run the circuits that I ran using NEAT, if you run the same circuit, what is giving you 0.85, can I make it 0.1? Maybe not. Maybe not. Code efficient on new logic for analysis makes different output. I'm not sure I follow this question. Code efficient or new logic for analysis. I mean, if you make your code more efficient, maybe ZNE will run faster, but not sure how something else will happen and what extra analysis do you want? I mean, the analysis that we did are something that is trying to validate the result. Is it close enough to the ideal result? But what extra analysis do you want? That is not very clear to me. Yeah, there are many quantum error correction algorithms, of course. I mean, oh, okay. So, yeah, okay. I mean, if you just ping me on LinkedIn, that will be great. We can talk over there, or we can see, take it up. I mean, this is for this paper on classical and quantum. So there are many quantum error correction algorithms. So this Hamming code and all these are classical error correction. But when you go to quantum error correction, it starts with basic repetition code, and then you go to say things like Steam code, Shor code, Laflamme code. These are very basic codes that we have. On top of that, next we have the surface code, which is very good for this 2D architecture thing. And a variant of the surface code is the heavy hexagonal code, which is particularly designed for the heavy hex structure of IBM devices. But now we are moving towards LDPC codes, which have been shown to have the performance of surface code. Surface code is very performant. LDPC codes are shown to have the performance of surface code, but requires way lesser qubits. So yeah, that's a huge, vast area of discussion itself, and I'm sure it will be covered in one of the. I mean, I hope if not this QT, some QTs. I'm sure it will be covered.
So no more questions are there. So thank you so much, Ritajit sir. Thank you for
Thanks.
taking your time out and having this insightful session. Definitely, these sessions have been fruitful for all the or most of the participants. Okay, if you want to explore it further, you may ping Ritajit sir on LinkedIn. There you may have further discussion. And and I would like to thank all the participants who were continuously engaged in this discussion. So definitely this engagement makes any session basically elaborative and fruitful. So definitely I thank all the participants for this engagement session. And Lastly, I would like to thank Dr. Ritajit Majumdar sir for this insightful session. Thank you so much, sir, for joining us. Uh,
Yeah,
so
thanks a lot. Thanks a lot.
yes, sir. So there are no more questions, sir. So we may stop the session here.
Okay, bye then.
Thank you, sir. Bye, sir.